When you see something like ChatGPT write a whole paragraph, or translate a language, or even spit out code, you gotta wonder, how does it do that? Well, the secret is this incredible architecture called the transformer. And today, we're gonna break down the one single idea that pretty much changed everything for AI. Alright, let's start with a little test. The chicken didn't cross the road because it was... Now what comes next? Tired? Or maybe too wide? See, for a human, that's easy. But how does an AI know what it is even talking about? Is it the chicken? Or is it the road? This simple question is actually a huge deal. And believe it or not, this right here, this super simple problem of figuring out what it refers to was a massive, massive roadblock for older AI. They just couldn't do it well. They'd get lost trying to connect words that were even a little bit far apart in a sentence. And that fundamentally crippled their ability to truly understand language. So to really appreciate just how brilliant this new approach is, we first have to look at the old way of doing things. Before transformers came along, the undisputed kings of language AI were these things called recurrent neural networks, or RNNs for short. Okay, so here's the difference in a nutshell. RNNs, they had this really linear, one-track mind. They would read a sentence one word at a time, trying to pass this tiny little scrap of memory from one word to the next. But transformers? Whoa! They just look at the entire sentence all at once. It's like having a bird's eye view of the whole conversation instead of just looking at one person in a single file line. And that, right there, is an absolute game changer. So what was the fatal flaw for these RNNs? Well, it was something with a really fancy name, the vanishing gradient problem. But don't let the name scare you, the idea is actually super simple. Just think of that game of telephone you played as a kid. The context from the start of a sentence is like the original message. It gets whispered from one word to the next, and by the time you get to the end of a long sentence, that original message is just a garbled, faint mess. The model has literally forgotten how the sentence even started. Okay, so the stage was totally set for a revolution. And boy, did it arrive. In 2017, a team of researchers from Google dropped a paper with this deceptively simple, almost poetic title. This paper, it introduced a mechanism so powerful, so incredibly effective at understanding context, that it just blew the old, slow, one-word-at-a-time structure of RNNs completely out of the water. They didn't need it anymore. And that powerful new idea? It's called self-attention. Alright, let's really get into this. I know self-attention sounds kind of abstract, right? A little weird. So to make it all click, we're going to use this absolutely brilliant metaphor. Just imagine that every single word in a sentence is an expert, and they're all sitting together on a console. Now to figure out how they should all work together, each of these word experts comes prepared with three things, just three things to remember: a query, a key, and a value. First up is the query. The query is basically the question a word needs answered. It's the word it in our chicken sentence kind of raising its hand and shouting, "Hey, I need some information here. Who in this sentence can tell me what I'm actually referring to?" Next, we have the key. The key is like each expert's name badge or the sign they put on the table in front of them. It's what each word advertises about itself. So the word chicken holds up a sign saying, "Psst, over here, I'm a potential subject." And the word road holds up its own sign saying, "Hey, I'm a noun too. I could be what you're looking for." And then finally, there is the value. The value is the actual stuff the expert has to say. It's the real information, the substance that the word chicken can share if it gets picked to answer the query. It's the payload. So this whole council of experts thing, how does it actually work? Well, what's so cool is that this isn't just a nice little story to help us understand. This metaphor maps directly, one-to-one, onto the actual math that's crunching away inside the transformer. Alright, let's walk through how the council makes a decision. It's a four-step process. Step 1, a word. Let's say our word it takes its query and compares it to every other word's key. This gives you a similarity score. How much do these two words vibe? Step 2, you scale those scores down a bit. Step 3, you run them through something called softmax. Now that's just a fancy math trick to turn all those messy scores into nice, clean percentages that all add up to 100%. These are the magic attention weights. They literally tell the word it exactly how much attention it should pay to every other word. And finally, step 4, you take those percentages and you multiply them by each word's actual value. And bam, you've blended all that information together. And the result of all this is the crucial takeaway. The process creates a brand new, souped up version of every single word in a sentence. So the word it isn't just it anymore, now it's it. That's probably talking about the chicken. And the craziest part, this happens for every single word, all at the exact same time. It's a total parallel operation. But, and here's where things get really, really wild. This whole attention thing, it's not just some clever programming hack that someone stumbled upon. No, it turns out this mechanism is actually tied to some incredibly deep, fundamental truths in mathematics. So, recent research has found something that is honestly mind-blowing. It turns out the entire transformer architecture, the whole thing, can be described by a type of equation that you'd normally see in physics. We're talking about the math used to model really complex, evolving systems in the real world, like how heat flows through a room or how particles interact with each other. Now, you absolutely do not need to understand this math to get the wow factor. Here's what this really means. Transformers aren't just some random assortment of computer science tricks that happen to work. It's more like they are a digital echo of a natural, continuous process that actually exists in the universe. It suggests that this architecture isn't just a lucky guess. It's like we've stumbled upon a fundamental pattern for how information itself wants to interact. So, there you have it. The attention mechanism gave AI a powerful long-range memory. It gave it a way to see and connect the dots across an entire idea all at once, solving that terrible memory problem that held back the older models. It is, without a doubt, the bedrock of the entire AI revolution we're living through right now. Which, of course, leaves us with one final, very big question. What's the next great limitation? And what will the breakthrough be that finally solves it? Back in 2017, a group of researchers at Google dropped a paper with a surprisingly simple, almost playful title. But attention is all you need wasn't just some new trick. It completely shifted the path of artificial intelligence, laying the foundation for the tools you and I use every single day. So let's dive in and break down the paper that really did spark the AI revolution. Alright, but before we get into the nitty-gritty, let's start with a really basic question. Think about it. When you read a sentence, your brain just gets it, right? It connects all the words together effortlessly to understand the full meaning. But how on earth does a machine pull that off? Believe it or not, for a long, long time, this was a huge roadblock for AI. You see, before this paper came along, the AI models that worked with language had a major bottleneck. They read things sequentially. It's kind of like they were forced to read a book one single word at a time. And the big problem? A terrible short-term memory. By the time the models got to the end of a long sentence, they'd pretty much forgotten what was said at the beginning. Not great, right? And this really breaks it down perfectly. On one side you have us, humans. We just scan the whole thing and we instantly get the context. But then you have the old way, using something called recurrent neural networks, or RNNs for short. And they were stuck in this one word at a time grind. One word, then the next, in a super strict order. You can see how, in a long sentence, the beginning just gets lost in the fog. So, you can probably guess this whole sequential thing was a massive drag. First off, it was slow, painfully slow, because you couldn't process the words at the same time. And then there was the memory problem. It was just terrible at connecting the dots between a word at the start and a word at the end. And this wasn't some tiny little bug. No, this was a fundamental wall that was holding back the entire field. But then, the authors of this paper came along with a completely different idea, a revolutionary one, really. They asked, what if we stop forcing the AI to read word by word? What if, instead, it could just look at the entire sentence at once and figure out which words are most important to which other words? What if all it had to do was pay attention? And that is exactly what they did. They went all in on this mechanism called self-attention. And the idea behind it is actually brilliant in its simplicity. Imagine for every single word in the sentence, the model creates a little scorecard. It scores how important every other word in that sentence is to it. So you're not just reading a list of words anymore. You're building this incredible dynamic map of meaning for the whole sentence, and you're doing it all at once. And this quote right from the abstract of the paper, this is where things get really wild. They didn't just bolt attention onto an old model. No, they did the opposite. They threw everything else away. No more of that sequential, one word at a time stuff. No more of these other complex techniques called convolutions. They built something totally new, from the ground up, based solely on this idea of attention. And what do they call this new architecture? The Transformer. This is the name you need to know. It's the blueprint, the engine that powers pretty much every single large language model you've heard of today. So yeah, let's pop the hood and see how this thing works. Okay, here it is, the famous Transformer architecture. I know, it looks a little intimidating, right? But don't worry, it really boils down to two main jobs. Over here on the left, you've got the encoder. Think of this as the reading part. Its whole job is to take in the input, let's say a sentence in English, and just understand it. Then that understanding gets handed over to the decoder on the right. This is the writing part. It takes that understanding and uses it to generate the output. Maybe that same sentence, but now translated into German. And look, what's right there in the guts of both sides? That multi-head attention. That's the powerhouse making it all happen. Okay, so the real magic, the secret sauce, is this thing called multi-head self-attention. Instead of just having one pair of eyes read the sentence, imagine the model has multiple heads, each looking at the sentence with a different specialty. So one head might be the grammar nerd, right? Tracking which subject goes with which verb. Another head could be like a detective, tracking who he or she refers to. The key is they're all doing this at the exact same time, in parallel. Then they pool their notes together to get this incredibly rich, layered understanding. It's brilliant. Alright, this slide's a little more in the weeds, but it really shows you the genius here. So that block on the left, that's the basic building block. That's one single attention calculation. But the real aha moment, which you see on the right, was them realizing, hey, why stop at one? We can run a whole bunch of these at the same time, in parallel. Each one of those blocks is a separate head. Then you just stitch all the results together, and boom, that's multi-head attention. It's what gives the Transformer both its power and its speed. And get this, the original Transformer model used 8 of these heads. So stick with that analogy of a team of experts. It's literally like having 8 different specialists looking at the same sentence, all at once. You've got your grammar expert, your pronoun tracker, your idiom specialist, all chiming in. By putting all their brains together, the model gets a picture that's way, way richer than any one of them could have come up with on their own. Okay, now this table from the paper, this is basically the mic drop. It's comparing self-attention to the old ways. And I want you to look at one thing, maximum path length. That's basically how many steps it takes for the model to connect two words. With the old RNNs, the longer the sentence, the more steps it took. But with self-attention, look at that. It's O of 1. Now that's just a fancy way of saying it's always one step. Let that sink in. It means a word at the very beginning of a paragraph and a word at the very end are, for all intents and purposes, direct neighbors. This wasn't just an improvement, it was a total game changer. So, we've got this amazing theory, this elegant architecture, but the big question is always, did it actually work in the real world? Well, the results they published weren't just good. They weren't even great. They were, frankly, world-changing. This is what kicked off a whole new era for AI. So the main test they put it through was machine translation, which has always been a super tough nut to crack. The way they measure success is with something called a BLEU score. All you need to know is higher is better. Now look at this. On the notoriously tricky English to German translation, the absolute best score anyone had ever gotten was 26.36. The Transformer, on its very first try, it hit 28.4. Yeah, let's just stare at that number for a second. An improvement of over 2 full BLEU points. Now I know 2 points might not sound like a headline, but you have to understand, in this field, researchers would fight tooth and nail for a 0.1 improvement. Getting over 2 points in one jump, that's like breaking the sound barrier. It was absolutely unheard of. It wasn't just a step forward, it was a giant leap into a whole new world. So the conclusion was just undeniable. The Transformer wasn't just better in quality. It was also way faster to train because this whole attention thing is perfect for running on modern GPUs. And if it's faster to train, that means it's cheaper to run. So you've got superior quality, more speed, and lower cost. Better, faster, cheaper. That's the holy trinity right there. That's how you kickstart a revolution. And the legacy, I mean, it's all around us. Just a year after this paper dropped, what came out? The very first model of something called a generative pre-trained transformer. Sound familiar? Yep, GPT. It was built directly on this work. And today, That exact same fundamental transformer architecture is the bedrock for pretty much every large language model you've ever used or even heard of. It all goes back to this one paper. You know, in the end, that playful title, Attention is All You Need, turned out to be almost prophetic, didn't it? For this particular revolution, it really was the one simple idea that changed everything. And that just leaves us with one last really big question to chew on. If attention was all we needed for this breakthrough, what's the simple, powerful idea that's going to be all we need for the next one?